If a planet has an atmosphere, it's considered potentially habitable. That's how astronomers have assessed TRAPPIST-1e. Among all the known planets, it stands out as one of the most remarkable outside our solar system. In 2023, with the help of the James Webb Space Telescope, astronomers observed TRAPPIST-1e 4 times as it passed in front of its host star. Based on the data collected up to September 2025, the Astrophysical Journal Letters published 2 significant studies, deeply analyzing the characteristics related to the surface and the potential for an atmosphere on TRAPPIST-1e. We'll delve into these findings to uncover what James Webb is revealing about this distant world. TRAPPIST-1 is a red dwarf star located about 40 light-years from Earth. Between 2016 and 2017, astronomers discovered 7 planets orbiting this star, all with sizes similar to Earth. This is the star system with the most rocky planets and the most similar to our solar system ever discovered. As a result, it quickly became a favorite among astronomers and is often called a miniature version of our solar system. What's particularly striking is that even the farthest planet in the TRAPPIST-1 system is much closer to its star than Mercury is to our Sun. This outer planet is only about 0.6 astronomical units AU from its star, whereas Mercury is 0.4 AU from the Sun. This comparison highlights how incredibly compact the TRAPPIST-1 system is, with planets packed tightly together in a very small space. The reason for this unique structure lies in the nature of the host star itself, a red dwarf much smaller than our Sun. Even among red dwarfs, TRAPPIST-1 is one of the smallest and is often classified as an ultracool dwarf. Its mass is only about 9% of the Sun's mass, small enough to allow planets to exist at very close distances without being excessively heated. Because the host star is small and has low luminosity, some of the TRAPPIST-1 planets can still reside within the habitable zone, despite orbiting so closely. Current assessments suggest that 3 planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, receive enough energy from their host star to potentially maintain liquid water on their surfaces. Due to this unique potential, these 3 worlds have become prime targets in the search for habitability within the TRAPPIST-1 system. When assessing a planet's habitability, the first and most crucial prerequisite is the existence of an atmosphere. A sufficiently dense atmosphere allows a planet to retain heat, maintain necessary surface pressure, and prevent liquid water from evaporating too quickly into space. This allows water to exist sustainably on the planet's surface. Therefore, even if a planet is within the orbital habitable zone, the first question science must answer is whether it actually possesses an atmosphere. So, how can we detect the atmosphere of a planet dozens of light-years away? Currently, the most effective and widely used method is spectroscopy. The principle behind this technique is relatively simple. When a planet transits or passes in front of its host star, some of the star's light passes through the thin atmosphere surrounding the planet. If the planet has an atmosphere, molecules within it will absorb some of the light at specific wavelengths, leaving characteristic absorption lines in the observed spectrum. Importantly, this absorption process isn't random. Each type of molecule, from water vapor to carbon dioxide or methane, leaves its own unique spectral signature. Thanks to these subtle signs, astronomers can infer the existence of an atmosphere and its chemical composition, even for worlds very far from Earth. To better visualize this process, let's look at an illustration of how the spectrum changes during a transit. Before the planet enters the transit phase, the spectrum of light from the host star is nearly flat. However, during the transit, as light passes through the planet's atmosphere, molecules like water vapor, carbon dioxide, or methane absorb light at their characteristic wavelengths. As a result, absorption lines appear as dips in the spectrum. These are subtle but scientifically valuable indicators. By analyzing the shape of these absorption lines and their corresponding wavelengths, astronomers can determine not only whether a planet has an atmosphere, but also infer the chemical composition of that atmosphere. Before the James Webb Space Telescope began observations, the prevailing view was that TRAPPIST-1e had a very low chance of retaining an atmosphere. This was due to the nature of red dwarf stars, which are very active and frequently emit intense bursts of radiation, far more violent than those from our Sun. Combined with the fact that TRAPPIST-1e orbits very close to its host star, scientists worried that this high-intensity radiation might have gradually stripped away and blown the planet's atmosphere into space. However, the data obtained from 4 consecutive observations by James Webb in 2023 paints a more complex picture. The transit spectrum of this planet wasn't entirely flat, as expected for an airless world. Instead, it showed certain fluctuations. Notably, in the wavelength range of 26 to 33 microns, researchers observed a signal that could be related to methane. However, these features weren't clear enough to draw definitive conclusions. As a result, TRAPPIST-1e finds itself in a gray area, suggesting the possibility of an atmosphere but not convincingly enough to rule out other causes completely. These ambiguous features in the spectrum have made decoding this exoplanet particularly challenging. The observed fluctuations could be either signs of an actual atmosphere surrounding the planet or products of other sources of interference. If these variations originate from TRAPPIST-1e itself, it would be compelling evidence for the existence of an atmosphere. However, the problem is that the source of the signal doesn't necessarily have to come from the planet. TRAPPIST-1, the host star of this planetary system, is very different from our Sun. Its surface temperature is significantly lower, only around 2,200 degrees C. In such conditions, the star's atmosphere isn't fully ionized into plasma, but still contains many gas molecules combined with complex activity on the star's surface, such as sunspots, bright regions, or magnetic field fluctuations. The light emitted from the host star can also carry similar spectral variations. Therefore, the fluctuations we observe could be traces of the host star itself, rather than reflecting the atmosphere of the planet orbiting it. To trace the true origin of the methane signal from those observations, astronomers have developed detailed models simulating the potential atmosphere of TRAPPIST-1e. These models carefully consider key factors such as the amount of radiation from the host star, the intensity of ultraviolet rays, and the mechanisms that could destroy methane over time. From this, a promising scenario has emerged. If TRAPPIST-1e does indeed have a methane-rich atmosphere, this world may bear similarities to Titan, Saturn's moon, where methane is maintained by continuous replenishment sources. This opens the possibility that TRAPPIST-1e is still geologically active, with processes like volcanism contributing to sustaining its atmosphere. Current simulation results aren't yet sufficient to draw definitive conclusions, and some of the observed signal may originate from the complex activity of the host star itself. However, importantly, there's no strong evidence to completely rule out the possibility that this exoplanet still retains an atmosphere. The observation time of the James Webb Space Telescope so far has been quite limited, not yet covering all the subtle variations of this star system. Longer observation campaigns in the future will provide more data, helping scientists gradually separate the planet's signal from the background noise of the host star. Therefore, even though the past 4 transits haven't provided a definitive answer, they have achieved something even more important, keeping the door of hope wide open. TRAPPIST-1e hasn't been removed from the list of worlds that may possess an atmosphere. And who knows, in the next observations, this small planet may offer the first clue about an atmosphere silently existing around a distant world beyond our solar system. That concludes today's science video. Thank you for watching.